Here we have a few examples to practice working with discrete random variables. So this first example, they give us a scenario. So we have a deck of cards. If you get a red card, you win nothing. If you get a spade, you win $5. For any club, you win $10. And if the card is an ace of clubs, you get an extra $10. So what we want to do is create a probability model with this idea that we have these different scenarios for how much money we can win, and attached to each of those is a probability coming along with the type of card we draw. So to make our probability model, we're going to have X, and then we're going to have these probabilities. So we're making this model for the amount that you win. So what we're making the model for is our X value. So X has to represent the possible amounts of money that we can win. So that's going to be our money part. So the idea is we could win nothing. So we could leave with $0. And that's going to be the idea of drawing a red card. We could leave with $5. And that's going to happen if we draw a spade from the deck. We could leave with $10 if we get a club. And our last scenario is specifically if we get the ace of clubs. The idea is that we get extra $10. So we already get $10 if it's a club, and then we get an extra $10. So we'd leave with $20 if we draw that ace of clubs. So the amount of red cards to get this probability, we want to think about how many red cards are in the deck out of all 52 cards. So in a deck of cards, there's 26 out of 52. And we're going to want a decimal in here, or you can use the fractions, but that would reduce to a decimal of 0.5. Spades make up of 1/4 of the deck, or there are 13 cards out of the 52. So that would be our 0.25. Now, with these last two scenarios, there's an overlap. And what we want to remember is that when we add these up, it has to add up to 1. So what we can't have is counting the ace of clubs twice. So the idea being, ace of clubs, we could actually calculate that first. That's only 1 card out of all 52 cards. And that would give us a decimal of 0.0192. So when we pick that specific card, we get $20. Then for all of the other clubs, it's $10. So we used up one of the clubs, and then there's this idea of 12 clubs are remaining out of all 52 cards. So this would have a decimal of 0.2308. And then once you finish making your probability model, just add up those probabilities and double check that they all add up to 1 to represent 100% of our sample space. So once we have this model, we want to find our expected value. So expected value, we take each data value times its probability, so 0 times 0.5, and then plus 5 times 0.25, plus 10 times that 0.2308. Or if you use the fractions here, those would give more accuracy either way. And this would give an expected value of 3.942. So that's the expected amount that we'll win. For the standard deviation, this is where we need a big square root. And then we're going to take each value minus the mean squared. So for instance, 0 minus that 3.942 squared. And then you multiply it by its probability. And then add that with the next value, so taking 5 minus that mean squared times its probability, and then add on 10 minus that mean squared times its probability, and then plus that last case of 20 minus that 3.942 squared times its probability, all under a big square root. If we calculate that, that would give us a standard deviation of 4.6336. So these two values together tell us that we expect to win $3.94, and on average, this deviates by this $4.63. Now this can sound strange because our expected value is actually less than the standard deviation. So we're saying we expect this much, but that can kind of change by 4.63. What happens with this is that it's basically saying 0 has a high likelihood. It's just confirming that, yeah, half the time we leave with nothing. So while we expect this 3.94, but it can deviate by 4.63, it's just saying that 0 is a likely outcome. So it can feel strange when this scenario occurs, but it's absolutely correct. For our next example, we have an incomplete probability model. So first thing we need to do is put it together. So they have this number of repair calls, and then these probabilities for each hour. So what we want to do is look at, okay, so far we've covered 0.1 plus 0.3 plus 0.4. So far we've covered 0.8 of our probability model. What's key is that all of these have to add up to 1 in the end. So if you take 1, take out that 0.8, what we're going to need right there for that 3 is a probability of 0.2. So you just need to fit the pieces of the puzzle so that it adds up to exactly 1. Expected value, take each outcome times its probability. So 0 times 0.1 plus 1 times 0.3 plus 2 times 0.4 plus 3 times 0.2. And that'll give us an expected value of 1.7, and our units here are in terms of number of calls per hour. So we expect 1.7 calls per hour. For standard deviation, we're going to have a big square root, and then you take each value minus its mean squared times its probability. So going through each value minus that mean that we calculate times that p of x. And get that last one in there. So 3 calls minus that 1.7 calls squared times its probability, and all of that underneath that square root. And that would be a standard deviation of 0.9. So that's telling us that we expect, or the shop expects, 1.7 calls per hour. And on average, this deviates by 0.9 calls per hour. So this last question says, what's the probability of being within 1 standard deviation of the mean? So something we can do with these probability models is where we have these discrete probabilities for each case, we can combine them to talk about probabilities for different scenarios. So looking at being 1 standard deviation within the mean, let's make a number line where we have our different cases. There's a case of 0, and then 1, 2, and then 3. I drew that a little too long. We have these 4 cases. Now our mean is landing at 1.7. So in terms of this number line, there's our expected value. Then we want to go 1 standard deviation below, 1 standard deviation above. So our distance for 1 standard deviation is that 0.9. So we want to go a distance of 0.9 below. So basically we're taking 1.7 and then take away that 0.9. And what that's going to do, it's going to kind of create this lower barrier for being 1 standard deviation below, and that's landing at 0.8. And then we need to do the same thing on the other side. To be within 1 standard deviation, we go below, but we also have to go above. So taking 1.7 plus 0.9 to kind of get this upper barrier for what's landing within 1 standard deviation. And that's going to be landing at 1.7 plus 0.9 is a 2.6. Now with our probability model, we have these discrete cases. We can have 0, 1, 2, or 3. We can't see these decimal cases. So to be within 1 standard deviation of the mean, really we just want to see which of these cases fit that scenario. And what we can see is 1 fits in that range and 2 fits in that range as well. So because those 2 cases fit, those both match up with the idea of being within one standard deviation of the mean. So for probability, we want to add those probabilities together. We want to take that probability of 1 occurring plus that probability of 2. So you're taking that 0.3 plus 0.4 to get this probability of 0.7. So there is a 70% chance of being within one standard deviation of the mean. So those are some different things we can do with these discrete random variables.